Hello everybody! I hope everyone's having a wonderful day. So I'm going to be doing another example involving logarithms with you today. So I'm going to be invoking a fact that I have not proven for you. I proved a version of this with integers. But I think that if you have some tools at your arsenal, such as calculus, things such as limits and series analysis, you can actually prove this statement in a straightforward fashion. I'm not going to be doing that here. Instead, I want to just invoke this fact, and I'm going to use that to prove a claim that actually is surprisingly helpful if you want to deal with polynomials with so-called exponents that are of fractional values or just whole values. So this actually will be a little bit more of a general statement than the one actually I proved in another example, where I just had it whereas log base 2 of n is big O of n. I'm going to be doing it for any epsilon, where epsilon is going to be any real constant greater than 0. So just to restate what we're going to be proving is that for any real constant epsilon, which is going to be strictly positive, I'm going to prove to you that log base 2 of n is big O of n to the epsilon. Sorry, I'm just getting really excited here. I'm serious. So what we're going to do is so this is the kind of idea I want to use. So I'm going to try using this fact, and I'm going to try to work that into my proof, and you're going to see why I'm going to invoke it in this way, because it makes things actually quite nice and easy. So if you are convinced by this fact, then we can quickly prove this statement, and that's what I'm going to do here. So what do we normally do? I tell you what I'm going to do, the game plan. To prove the claim, we compute constants. How many constants? There's 2 of them, right? C, which is a positive real number, and n0, which is a positive integer, right? So that for all n greater or equal to n0, it must be that log base 2 of n is less than or equal to c times n to the epsilon. So that's the game plan. So I'm going to select a c, and you'll see why I'm going to pick this particular c in a moment. I'm going to actually invoke a couple of things that we've actually seen in the past. We're going to be using the power rule of logarithms to prove this claim. And then by using that, you're going to get an intuition quite quickly of one little trick I'm going to do with exponents. So check this out. This is actually going to be quite nice and slick. So I'm going to select c is going to be equal to 1 over epsilon. Then we find n0 such that log base 2 of n is less than or equal to 1 over epsilon times n to the epsilon, right? And this has to be for all n greater or equal to n0. So I want you to take a look at the left-hand side of that inequality. So what I would like to do is I would like to get something that looks like 1 over epsilon that sits somewhere on the left-hand side of that inequality. Now watch this. This is going to be using properties of exponents. So watch this little trick. Notice by invoking the power rule of logarithms, that log base 2 of n is going to be equal to the following. Now watch really closely what I'm going to do here. That log base 2 of n to the epsilon raised to the power of 1 over epsilon. Now, if you remember your properties of exponents, if I have epsilon here, if I raise all of this to another power of another exponent, it ends up actually turning into a product. So I'm going to multiply these two exponents together, and that would be epsilon times 1 over epsilon is 1, right? That's why this equality actually holds. And it holds especially that we know that epsilon is in fact not going to ever be 0. So we're okay. So what can I do with this now? Well, I have this term here, but I have this exponent here. Maybe I can use the power rule to pull that out in front. So by the power rule, I can write this out now as 1 over epsilon times log base 2 of n to the epsilon. So now I have something that looks like a 1 over epsilon times a something is less than or equal to 1 over epsilon times n to the epsilon. Now watch this. So watch this. Since, sorry, that melted in the microwave a little bit. Since log base 2 of x is less than x for all positive reals, then all I'm going to do is I'm going to substitute in for x n to the power of epsilon. Because n to the power of epsilon will be a real number guaranteed, right? Then log base 2 of n to the epsilon is less than n to the epsilon for all n greater or equal to 1. For all n greater or equal to 1. And the following has to be true. And thus, let's put it all together. For all n greater or equal to 1, log base 2 of n is equal to 1 over epsilon times log base 2 of n to the epsilon, which is less than or equal, because of this inequality here, is less than or equal to 1 over epsilon times n to the epsilon. So what should I select for n0? I should select 1. 1 or higher will work. Select n0 is equal to 1. Therefore, we're done, right? Therefore, for all epsilon greater than 0, by the definition of big O, log base 2 of n is big O of n to the epsilon. And we're done. Boom! Nice and easy. So you'll notice here that I just use some properties of logarithms and the fact that I know this for logarithms for all real numbers. Now, you might ask, Dan, what would I want to use this for? Well, like I said, it's quite a broad statement. For example, if I make epsilon equal to 1/2, then this is actually me saying that log base 2 of n is big O of square root of n. So this is an alternate way of proving this claim. So this is a way without needing to use limits. However, like I said, this statement is doing all the heavy lifting for our proof. I want to say thank you very much and have yourself a beautiful day. I'll see you later. Bye-bye. I'll see you later.